All right, so carrying on with parabolas, we're going to look at a specific parabola which is centered with its vertex at the point 0, 0. So the vertex of this parabola here is 0, 0. And what I want to do is say that the focus is at some point above and the directrix is a horizontal line down below. And that is the same distance on either side. That distance there and that distance there is going to be the same. So to make this kind of general, so that we can come up with a generic equation for a parabola, what I want to do is go ahead and just not specify what that distance is, but use a letter to represent it. So we're going to use the letter P. This is traditional. Most textbooks use the letter P for what's called the focal length of the parabola. Focal length. And that's just the distance from the focus to the vertex, which is the same as the distance from the vertex to the directrix. So now, if we have a point somewhere on this parabola, let's call it point xy, let's have that be a variable point. It could be anywhere on this parabola. The distance back to the focus and the distance down to the directrix should be equal to each other. So I'm going to call those distance 1 and distance 2. And we're going to say distance 1 equals distance 2. Okay, that fact should define the parabola. And so we're going to use that to come up with an equation for this parabola. In order to do that, I'd better write down the coordinates of the focus. So this focus here, if it's p units above the vertex, and the vertex is at point 0, 0, then this should be at point 0 p. I hope that's comfortable to everybody. P units above 0 would be p, y equals p, right? And this directrix, by the way, is down here at y equals negative p. So let's get that information in. So now let's calculate what d1 and d2 are individually, and then we'll set them equal, and then do a bunch of algebra to try and figure out what the equation would be. Okay, so d1, the distance from xy to 0p. Well, we can use the distance formula, right? xy to 0p. So let's start with x minus 0 squared, and then plus y minus p squared. I'm sorry, I wrote b, but that's meant to be a p right there. Minus p squared. So there's applying the distance formula to get the distance between those 2 points, just using their coordinates. Simplifying that up a little bit, x squared plus y minus p. Oh my gosh. I'm like vertically dyslexic or something. I don't know. X squared plus y minus p squared. There we go. So that's distance 1. Distance 2 is easier to calculate because it is measured along a vertical line. In this case, with our directrix being horizontal, all distances to the directrix will be measured along horizontal, vertical lines. So we just need to take the y coordinate, which is, just that distance, that's y coordinate, and then plus this amount, which is p. So that's just y plus p. All right, so now we've calculated the d1 and the d2 independently. That is for an arbitrary point on the parabola, right? So now all we need to do is set these equal to each other. So y plus p equals the square root of x squared plus y minus p squared. Actually, that is an equation for the parabola. So we could stop there if we wanted, but I think we want to go a little bit further than that. So let's take this, and we're going to try to solve this for y, or at least kind of move in that direction so that we come up with something which is relatively simple and easy to work with. Okay. So the first step I want to do is square both sides of this. Squaring both sides will cancel the square root, which is over the entire right side. And now we have the entire left side squared. I had to put the parentheses in there because of squaring the entire side, squaring that whole binomial. Remember, I can't just square each term individually because powers do not distribute over that addition. Okay, which is the same reason why this square root doesn't cancel these squares on the right. That doesn't happen because it doesn't distribute over the addition. But at least having squared both sides, I've now gotten rid of that radical. I think the next thing I want to do is go ahead and expand these squares. So I'm going to do, you can FOIL this if you want, but you should end up with y squared plus 2py plus p squared on the left. And then on the right, we still have the x squared, but then this is going to be y squared minus 2py, but still plus p squared. All right? So we're getting really close, because now we can see that a bunch of stuff is going to cancel. If we subtract y squared from both sides, they both have a plus positive y squared, which will cancel out. And similarly, they both have a plus p squared, so we can subtract p squared, and that'll cancel out too. Next, we have a 2py and a negative 2py. Let's combine those like terms. I'm going to add the 2py to both sides. So it's going to cancel over here, but here, instead of canceling, they will add together. 2py plus another 2py will give us 4py. And on the right side, x squared is still there. And we're not going to go all the way to solving for y. We could divide by 4p if we wanted, but let's just leave it in this format because this is a nice simple format to have it in. This is the equation of a parabola with vertex at the origin, focal length p, oriented with a vertical, what's the word for that? A vertical, shoot, I forgot what this thing is called. This line here. Oh, axis of symmetry. I think that's the right word for it. It's got a vertical axis of symmetry. So in the next video, I'll just show how you can take this equation and modify it a little bit to make different parabolas.